Scientists thought Pluto was a frozen, dead world, until they discovered a massive, heart-shaped glacier that defied all expectations. What secrets does this icy heart hold? Pluto, once the 9th planet of our solar system and now classified as a dwarf planet, remains one of the most enigmatic celestial bodies in the Kuiper belt. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more dynamic and complex than anyone had imagined. One of the most striking discoveries was the presence of a vast, heart-shaped glacier that dominates Pluto's surface. This enormous region, officially named Sputnik Planitia, is a vast expanse of nitrogen ice that has puzzled scientists ever since its discovery. The heart-like shape, combined with the region's unique geological activity, suggests that Pluto is not the static, frozen world many once assumed. Instead, it is a place where glaciers flow, where convection reshapes the landscape, and where an internal heat source might still linger beneath the icy crust. This glacier is unlike anything seen in the solar system, a place where solid nitrogen moves like Earth's glaciers, reshaping Pluto's surface over millions of years. The formation of Sputnik Planitia remains one of the greatest mysteries of Pluto's history. This massive basin, spanning over 1,000 kilometers, is thought to have formed from a colossal impact in Pluto's ancient past. A giant object, possibly a Kuiper belt body, could have struck Pluto, carving out a deep depression. Over time, volatile ices such as nitrogen, methane, and carbon monoxide may have accumulated in this basin, creating the bright, reflective plane we see today. But this explanation raises new questions. Why does the ice remain so fresh-looking, with almost no impact craters? How does it maintain its distinctive shape? The answer may lie in Pluto's interior. Unlike other parts of the dwarf planet's surface, Sputnik Planitia appears to be in constant motion. Convection cells, driven by the slow churning of nitrogen ice, create a constantly renewing landscape. Large blobs of ice rise and sink over time, erasing old craters and forming a pattern of polygonal segments across the glacier's surface. This process is strikingly similar to what happens in Earth's mantle, where hotter rock cycles upward while cooler rock sinks. The presence of such activity suggests that Pluto, despite its distance from the Sun, retains enough internal energy to keep this process going. The role of Sputnik Planitia in Pluto's overall climate and atmospheric cycles is another area of intense study. Unlike Earth, where glaciers are composed of water ice, Pluto's glacier is made mostly of nitrogen. This ice plays a crucial role in Pluto's thin atmosphere, constantly exchanging gases. As sunlight strikes the glacier, some of the nitrogen sublimates directly into gas, replenishing the atmosphere. When temperatures drop, the nitrogen refreezes, creating a seasonal cycle of frost and ice movement. This delicate balance between Pluto's surface and atmosphere may explain why Sputnik Planitia remains so smooth and uncratered. Over time, the slow but persistent cycling of nitrogen could refresh the surface, covering any old impact scars. Scientists also believe that Sputnik Planitia influences Pluto's overall orientation. The glacier's immense weight appears to have caused Pluto to reorient itself, a process known as true polar wander. This means that Sputnik Planitia likely played a key role in determining Pluto's modern-day spin axis, reshaping the dwarf planet's very identity over millions of years. The discovery of Sputnik Planitia also raised fascinating questions about the possibility of an ocean beneath Pluto's icy shell. Some scientists propose that the impact that created the basin may have also exposed an underlying subsurface ocean. If Pluto once had a layer of liquid water beneath its crust, the impact could have disrupted it, allowing ice to form and accumulate in the depression. The idea of a liquid ocean surviving beneath the surface of a world so far from the Sun is astonishing, but not impossible. Recent models suggest that Pluto's interior may still hold enough heat, possibly from the decay of radioactive elements, to keep an ocean from freezing entirely. If such an ocean exists, it could hold clues to the chemistry of the early solar system and even the potential for some form of primitive life. While no direct evidence of this ocean has been found yet, the presence of Sputnik Planitia and its constant resurfacing suggests that Pluto's interior is far more active than previously thought. Despite its vast distance from Earth, Pluto and its heart-shaped glacier have reshaped our understanding of small, icy worlds. The New Horizons mission transformed Pluto from a mere speck in the sky into a complex, evolving world with glaciers, mountains, and a dynamic atmosphere. Sputnik Planitia, with its stunning shape and mysterious properties, remains one of the most captivating features of Pluto's surface. Its continuous motion challenges the assumption that distant, frozen worlds are geologically dead. Instead, Pluto appears to be a place of slow but persistent change, a world where ice flows like rivers, where atmospheric cycles breathe life into the landscape, and where an ancient impact may have left behind a hidden ocean. As scientists continue to analyze the data from New Horizons, new questions continue to emerge. What lies beneath Pluto's icy crust? How long has Sputnik Planitia been active? Could other distant worlds harbor similar processes? Pluto's heart-shaped glacier is not just a symbol of its beauty but a reminder that even the most distant corners of our solar system hold secrets waiting to be uncovered. Pluto's heart-shaped glacier is more than just a pretty sight. It's a window into the hidden forces shaping this distant world. What other surprises might Pluto be hiding beneath its icy surface?